بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. It is 8:30 exactly, so let's start inshallah. Yes, today we are going to start chapter 5. And chapter 5, what's the title?
Thermochemistry.
Thermochemistry. Thermochemistry. What are we going to talk about?
Fluids.
What? Thermochemistry. What's the meaning of thermo?
Heat.
Yes. So we're going to talk about chemistry, and heat. Or general, not only heat, and energy. So we're going to talk about chemistry and energy, which is heat or something else. It could be heat and it could be something else. Clear? Good. All right. So we're going to talk about energy, type of energy, and so on and so forth. Let's go to form of energy. First, energy, we have two types of energy. We have what's called kinetic energy, and potential energy. You've seen this before. Kinetic energy is related to what?
Motion.
Motion.
Motion, exactly. And potential energy.
Height.
What?
Height.
Position. Or height, level. All right? So yes, exactly. So these are two types of energy, and each one, they are convertible. We can change kinetic energy to potential energy or change potential energy to kinetic energy and so on and so forth. The easiest to think about is if you have, this means, okay, let's put it this way. Which one have higher energy? The one moving at slow motion, the one moving slowly or fast?
Fast. Fast.
Fast is higher energy. Good. If we have potential energy, if we have two levels like this, which one has more potential energy?
The higher.
The higher. A or B, yes. If you go from A to B, what will happen?
Convert from potential to kinetic.
The speed will go up and something will come out of this energy. Good, that's exactly what I mean. No, now, this is called kinetic energy. It's related to motion. We know the law of kinetic energy. What's the law of kinetic energy?
Half mu squared.
What's E?
Energy.
Kinetic energy.
Kinetic energy. What's M?
Mass.
Mass.
What's U?
Speed or velocity.
P. Good. Very good. All right. Thermal energy. What do you mean by thermal energy?
The heat.
Heat energy. We're going to call it from now on as Q. Q. Is Q kinetic or potential? Q is related to the motion of the molecules or atoms. Motion of the molecules. So is Q kinetic or potential energy?
Kinetic energy.
Kinetic.
Kinetic.
Why?
Because motion.
Related with motion of the molecules.
So this is kinetic energy. Clear? Good. Now, and that's why, how can we measure Q? By temperature. The motion is, we can measure it by temperature. Good. Potential energy, as we said, potential energy is related to height. All right, and this one having more energy than this one. It stores more energy in A compared to B. So there is more energy in A compared to B. Okay. The kinetic energy, chemical energy is potential energy. What's chemical energy? Is the energy stored with the structure unit, molecules, or polyatomic units of chemical substance. The chemical energy is the energy in the bonding and so on. So if there is a compound like A and B, chemical energy is related to the bond, the type of compound, is it gas or liquid or solid or things like that. All of this is called chemical energy. In this chapter, we're going to use the letter capital H to represent this chemical energy. Chemical energy is the H. What is it related to?
Chemical energy.
It is related to bondings, to the state of the matter, and so on and so forth. It's related to the bonding, bonds, and state of the matter, whether it is solid or liquid or gas. All right. What are we going to call this energy? What's the letter that we're going to use?
H.
H. Okay. Is this kinetic or potential?
Potential.
It is potential energy. Okay. This H, we're going to call it from now on as enthalpy. Enthalpy. I want you to know the name, memorize it very well. Enthalpy. Good. Okay, we have also electrostatic energy. Electrostatic energy, which is related to electricity. The electrostatic energy equal to Q1 times Q2 divided by D, or it's a constant related to Q1 is the charge on one of the atoms, and Q2 is the charge on the other atom, and D is the distance between them. So if I have, for example, sodium Na bonded to bromine, Br, and in A. In this case, what's Q1?
Na.
What? What's Q1?
Plus one, the charge difference.
What's Q2?
Minus one.
Minus 1. So plus 1 times minus 1. Divide by, what's D?
Distance.
Which distance?
Distance between them.
Distance from the nucleus to the nucleus. Is this clear? So this is D. While if I put, for example, calcium 2 plus with oxygen O2 minus. Again, What is Q1 in this case?
Plus 2.
Plus 2.
Plus 2. What's what's the Q2?
Minus 2.
Minus 2 divided by
D.
which is this distance. All right. Okay. If let's assume that is not true, but let's assume that this distance and this distance is the same. Which one will have more electrostatic energy? Calcium oxide or sodium bromide?
Calcium oxide.
Why?
The same.
No, it's not the same.
Sodium.
Oxide have more. You can see here it's 2 times 2, which is what?
4.
From this,
-4.
and this one is 1. So which one has more energy, more electrostatic energy, calcium oxide or sodium bromide?
Calcium.
Calcium oxide. How much more?
3.
4.
4 times. 4 times. Okay, so if the energy for sodium bromide is A, okay, then what will be the energy of calcium oxide?
4A.
4A. That is if D and D are the same, if they are exactly the same. Good, excellent. Okay, good. Law of conservation of energy. What's the law of conservation of energy?
The energy can't be destroyed or created. It can be transformed from another form.
Energy cannot be what? Destroyed or
created.
so what will happen if we lose speed or anything? It will be always what?
Transfer.
Converted to something else. You can convert energy from potential to kinetic, from speed to energy, from speeding energy to potential energy. You can change energy from one form to another, but you cannot destroy it, nor you cannot create it. Good. Okay, now I'm going to define 2 things, very easy, and system and surrounding. What do I mean by system? You define, this is system. If this is your system now, what is your surrounding?
The around.
Everything else around it.
Anything around it is called surrounding. So in this case, this is the system, and this is the surrounding, or anything around it outside is surrounding. Okay, all right. Now let's have, if I have a piston here and this piston is moving, so if this piston is my system, what is the surrounding? What is the surrounding?
The rest of the universe.
Anything, yes, the rest of the universe. Exactly, good. All right. If the system moves like this, what happened to the system? How can you move from this side to this side?
Compressed.
Compressing.
Yes. How are you going to compress it? You have to put energy here to make it goes down, right? Right?
Yes.
So you have to put energy to go from this side to this side. So the energy was given from where? From the surrounding to the system. Okay? Good. All right. Now, Heat. What's the letter that we're going to use for heat?
Enthalpy,
No. Heat. No.
thermal energy,
Right?
Heat
K.
Q.
Q. I want you to memorize this. Heat, we're going to use Q. And Q, is it kinetic or potential?
Kinetic.
Yes,
Kinetic.
energy. Okay, good. All right. Okay, thermochemistry is the study of heat or heat transfer. Here, heat transfer from one system to the other thing, and that's called in chemical reaction. Okay, in chemical reaction, how the heat is happening. Okay, next. Now, chemical energy or chemical reactions are, if there is any change in the chemical reaction, we're going to use what's called enthalpy. Enthalpy for it. Not heat, enthalpy. What's the letter that we're going to use for enthalpy?
H.
H,
H. H. And you can, as I said, the H and Q can be transferred from one to the other, but this is enthalpy is what?
potential energy.
Potential energy. This is kinetic energy and this potential energy. Let's look at this thing here. A chemical reaction, if we have a chemical reaction like this one, 2H2 plus O2 goes to 2H2O liquid. All right. What happened here? Which one is at higher energy, or A or B?
A.
A,
A is higher energy, right? If you
Yeah.
go from A to B, like what happened here, what will happen?
You will lose energy.
Decrease.
Lose energy. The energy will come out as Q. Is this clear? The energy, if you go from A to B, you will lose energy. You can never, you will lose energy. You cannot lose energy. What will happen? It will be converted to something else. Is this clear? As we said, law of conservation of energy. You cannot lose energy, but the energy will come out as Q. The energy that you lost will come out as Q. Is this clear? Okay.
Yes.
Type, when you go from A to B, what type of energy you have there from A to B? Potential energy. What's the name for it?
Thermal energy.
No, it's not thermal energy. It's actually
Enthalpy.
thermal energy is Q. All right. So this is from you when you go to from A to B. This is called enthalpy. When you go from higher level to lower level from A to B, this is called exothermic process. Exothermic process. Clear? And like this, we write the equation 2H2 plus O2 to give you 2OH2 plus energy. Plus energy. Why? Because the energy come out like this. Is this clear?
Yes.
What will happen if I go from B to A?
You will gain energy.
Exothermic.
Okay. How can you go from A to B? Can you write a chemical equation for this for this product, if you go from B to A, what will happen? You need to go
H2O plus fire or energy.
plus energy. To go to what?
H2 gas, O2 gas.
2H2 gas plus
O2.
O2 gas. Exactly. And you will put the energy now with the reactant, not with the product. Okay. And in this case, what are we going to call this process? Second process. This one is called exothermic. What do you think the name of the second process?
Endothermic process.
Endothermic process. Good. Is this endothermic or exothermic process?
Endothermic process.
Endothermic. Why?
It
The
absorbs.
energy is in the reactant.
Because you are adding energy to make the reaction goes like this. So the energy is with the reactant to make the product. Good. This is called endothermic process. Good. Okay. Units. Very important to know the units. Okay. What's the unit for SI unit for mass?
Kilograms.
Kilogram.
Good.
Kilogram.
What's the unit mass for distance or
Meters.
for velocity? What's the unit for velocity?
Meter per second.
Meter what?
Per second.
Per second.
Good. Then what's the unit for energy?
Joule.
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 No, let's use the same units. We know that it is kilogram half mu squared. So what will be the unit? SI unit.
Kilogram.
Kilogram.
Kilogram. Meter square. Second square.
Second square. Kilogram meter square per second square. This is called joule. So what is a joule? What's a joule?
Kilogram meter square
by second square. All right, very good. You have to know this. Also, the joule is equal to 1 Newton times meter or Newton meter. So what is the unit for Newton, which is the unit for force? Kilogram times meter per second square. And that's how can you make Newton go to joule? So 1 joule is equal to 1 kilogram, which is N, I'm writing here, meter divided by second square times what?
1 meter.
Meter, which is equal to what? 1 kilogram meter square per second square, similar to the top, this one. Good? Very good. Okay, calculate the kinetic energy of helium atom moving at speed of 125 meters per second. Okay. What's the mass of one helium atom?
1.08.
Helium, not hydrogen.
4.003.
4.003. What's the unit?
Gram per mole.
No. Yeah, per mole. I'm talking about one atom.
gram.
ATM.
Wrong. Yes.
Gram.
ATM? What do you mean by ATM? Not ATM.
AMU.
Yes.
Convert it to moles, then to Avogadro's number.
You. AMU. How can you change AMU to gram? Always.
Divide by Avogadro.
Yes, exactly. You have to keep this in mind. 1 gram equal to what?
0.22.
Now, tell me what's the mass of one helium atom in gram. Quickly. Use your calculators.
Uh, 6.64 multiplied by 10 to the power 5.
6.649 times 10 to the power minus
24.
24 gram. Okay. In order to find the energy in joule, what should I do?
To kilogram.
Yes. So what should I do?
Divide by 1000.
So what will be the mass in kilogram? 6.649 times 10 to the power
Minus
27.
27 kilogram. Now tell me what's the energy. Of course, the energy equal to what?
times mv squared.
Okay, go ahead. Give me the final answer.
uh, 5.19
5.19
4.19
multiplied by 10 to the power minus 23.
minus 23.
23 joule. Exactly. Is this how the, oh, yes.
In first step, can we say that we are converting from one atom to 1 mole?
No, we're keeping one atom. We want the mass of one atom in gram. This is the mass of one atom in gram.
Yes, we can calculate the number of moles for one atom, then multiply it by the molar mass, and we can get the same answer.
Yeah, I know, but what will, if you multiply it by, this is the mass of one atom. The mass of 1 mole of helium, 1 mole of helium. What's the mass of 1 mole of helium?
I mean the number of moles for one atom.
The number, yeah, that's why I say 1 mole, the mass will be 4.003 gram.
Okay, thank you.
Okay, all right, good. B, let's solve B. Okay, if we have 2 nucleus, okay, we have, let's read it. How much greater the magnitude of electrostatic attraction between electron and nucleus containing 3 protons versus that between an electron and the nucleus containing 1 proton. 1 proton. So let's, I'll do B here. This is, by the way, we solved A here, and we're going to solve B here. B, we have a nucleus containing 3 protons and an electron, and another nucleus containing 1 proton, 1p, and electron. Which one will have more electrostatic force?
The first one.
First one, this one. Why?
The first
Why?
minus 3
What's the energy?
times minus 1.
For first one, E1 will be equal to what? Or proportional to what?
Q1 multiply Q2
E1
over
2. 1 times,
minus 1 times 3.
yes, minus 1 times plus 3 divided by what?
D.
D. And
We
this
have
one
the same
has the
D.
same distance. What's E2?
Minus 1 times 1 over D.
If the distance is the same, which one will be greater, the first one or the second one?
First one.
First
How
one.
much greater?
Third.
3
3 times. This one is greater by 3 times. That's all. 3 times. Good. So that's why the energy is 3 times. Good. Okay. Another unit that we're going to see, it's important unit also. It's called calorie. And the calorie is equal to 4.184 joule. Don't memorize this number. It's available. Look at your periodic table. It's available in your periodic table. But keep it in mind and keep it very well. Memorize it almost. 4.184. 1 calorie equal to 4.184. Capital C, which is 1,000 calorie with small c, and that's why 1 calorie is equal to 4,184 joule. This is for people who are doing diets and energy. They care about energy. But what I want you to know very well is a cal is equal to what? 1 calorie is equal to what? 4.184 joule. Look at your periodic table. Is this available in your periodic table? The one that I gave you.
It's the specific heat for H2O.
H2. Oh,
Only specific heat. They did not say calorie.
no.
Okay, but it is the specific heat of water exactly, because we're going to talk about this in a while. All right, but 1 calorie equal to 4.184 joule. Good. All right. Function. Okay. We have what's called open system, closed system, and isolated system. Okay, this is our system. We have 3 systems here. Which one is open system?
A.
First.
Why it's not open?
Because it's open to the air.
And
It's
you can
protected by the surrounding.
both amount, you can lose quantity and heat, right? You can lose amount and energy, right? Okay, then what's the B is called?
Closed system.
Closed system.
Closed. Why?
It can't lose
You can lose what?
mass.
No, you cannot lose mass.
Energy.
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 You can lose energy only. Yes, I prefer instead of amount, I prefer mass. Okay, so you cannot, no loss of mass. Okay, what's the last one called?
Isolated.
System.
Isolated system. You cannot lose
Either energy, either
Oh,
neither
no.
energy.
no energy is lost. Clear? Very good. That's the 3 types. Good. State of system. What's the state of the system? When we say the state of the system, we mean things like energy, temperature, pressure, and volume. These are the state of the system. So we can, if we have a gas in a container like this, and we expanded the room. Same gas, let's say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. What happened to the system volume?
Increased.
Increase. So we're keeping the same gas, the same amount, but I increase the state or the volume. In this case, the system state volume increase from one thing to the other. All right. Now, STP. What's the volume?
22.4 liters.
22.41.
Liter. Exactly. We call this 22.4 liter. We call it state function. State function. Not only state, this is the first one we talk about state. And now we say state function. This means it's very specific at a certain amount. This means if you are at STP, then the volume will be always 22.41, regardless how you get to this point. That's called state function. Is this clear? Okay, we will see this a lot in chemical reaction. Chemical reaction is always will have a certain energy stored in the chemical reaction. This chemical reaction has a state function. Q is not state function. Q is not state function. Okay, but H is what? State function. Okay, I wanted to know this very well. U is not state function, but H, which is the chemical energy, which is the enthalpy, is state function. Now, what's the meaning of state function? Things that have certain energy at certain conditions, and it will have exactly that energy or that volume at certain energy. In this case, I gave you the example of the gas. The gas will have certain volume at certain conditions. If you have 1 mole at STP, then the volume will be always 22.4. That's called state function. If you have any chemical reaction, in the chemical reaction, H is a state function, and it will be exactly the same always in that reaction. But Q is not state function, so Q can change if you change the chemical or if you do something with the chemical reaction. Good. Okay, first law of thermodynamics. First law of thermodynamics. What's the law of thermodynamics? First law of thermodynamics is the conservation of law of conservation of energy. What's the law of conservation of energy?
Energy does not destroy or create.
Energy cannot be what?
Destroyed or created.
Okay, so what will happen to it if it changes?
Converted from one form to another.
Exactly. So if you have a system, it has energy, let's say X, and you make it goes into another system, or you play with the energy of it and you make it change to Y, what will happen? It changes energy. Where the energy went, from where to where? If this is your system, then it will go from the system to the surrounding. Okay, so the energy of the system plus the energy of the surrounding must be equal to what?
Zero.
Why? Whatever you lose from the system, you will what? gain
in the surrounding.
in the surrounding, and as a result, law of conservation of energy. The total will be what?
0.
0. And on the other hand, if you gain here, what will happen here?
Lose.
Lose. And the total will be, again, 0, always. And that's why the delta U of system plus delta U of surrounding must be equal to 0. Or delta U of system is equal to what?
minus delta U.
The delta U of surrounding, but with a different sign. Clear? But that's called the first law of thermodynamics. First law of thermodynamics. Is this clear? Another way to say, or delta U is U final minus U I, or delta U surrounding plus delta U system must be equal to what?
0.
0.
0.
Exactly. Whatever you lose here and there, it is 0. Okay. All right. Energy is defined as capacity to do work or transfer heat. Energy is work and transfer heat. Work, we're going to represent it by the letter W. And heat will be represented by which letter? Q. All right. When system release or absorb heat, its internal energy change. Likewise, if you release or absorb heat, the internal energy, yes, I should say this. What's U? U is the internal energy. Okay. So U is the internal energy, the whole energy in the system. So when system absorb or release heat, the internal energy change, right? So if this is your system, and let's assume it has delta U1. If you lose, some heat goes out, you're going to change the internal energy. Okay, it will be now delta for the system. After that, delta U2. Which one is higher, delta U1 or delta U2?
Of course.
1.
1. Why?
Because it's always transfer from the higher to the lower.
Okay. Now, what will happen to delta U? This is the system. What will happen? Delta U1 surrounding now. Which one is greater, delta U1 surrounding or delta U surrounding 2?
2.
Which one is greater?
2.
2, yes. So this one now is smaller. I hope this is clear. So, and the same thing with work. When you do work in a system, it will internal energy will change. The first law of thermodynamics, first law, again, also can be stated like this. Delta U is equal to Q plus W. What's delta U?
Internal energy.
Internal energy. Internal. What's Q?
Thermal energy.
No. A thermal energy or heat energy or thermal energy. Very good. Yes. Heat energy or thermal energy. Thermal energy. Exactly. What's W?
Work.
Work. Good. Now, you have to keep these 3 letters in your mind. Very good. Now, and I want you to understand it very well. It's very easy. We are not going to memorize it. We have to understand it. When heat absorbed by the system from the surrounding, this means this is your system, and the heat will come from here to here. We'll call it Q. Okay? This heat, we're going to give it from the surrounding to the system. Then in this case, the Q, we're going to give it a positive sign. If the Q goes from the system to the surrounding, the Q will give it what sign? Negative. Clear? Okay. If the work done like this is piston now, and you change it from here to here. The work is done by what to what?
Compressed.
Yes. So work done by what?
Surrounding.
Surrounding on what?
The system.
System. So which sign we're going to give it?
Plus W.
Plus W.
It will be plus W. See, it's done by the on the system. By the surrounding on the system, we're going to give it plus. What will happen if it's by the system and the surrounding?
W will be negative.
Negative. So the first one is positive, this one is negative, this one is positive, this one is negative. You have to understand these things extremely very well.
Doctor,
Calculate, yes, just 1 second.
can you write? Can you draw a figure for the fourth state?
For the state?
The fourth condition for the table. Can you write? Can you draw a diagram?
For the last one, which is this one, for?
Yes, to imagine it.
I can draw it this way, going from this way to this way.
Okay.
Okay, so this is 3, if we put 3 here, and this is 4. If you do it by the system and the surrounding, this means the system forced the thing to go up, and it did work on surrounding. Good, let's solve this problem. Calculate the overall change in energy, delta U. Delta U is equal to what?
Q plus W.
Q plus W.
Yes. Very good. Okay, now what's delta U for this reaction? Let's read. For a system that absorb, what does the meaning of absorb?
Gain.
Then the system will take the energy from the surrounding. So is the sign going to be positive or negative?
Positive.
Positive, because it's absorb. What's the other word? What's the other word that we should use instead and to make it negative?
Release.
Okay. And of heat. And does 141 joule of work on surrounding. So what's the sign of W?
Minus.
Why?
Because the system does the work.
Because the system does the work on the surrounding. And you can calculate delta U, which is in this case 47. Is this clear? Very good.
Yes.
Now, first one. Is this cube greater than 0 or less than 0? First one.
Less than zero.
Less.
Why?
Release.
Release, exactly. Release from system to surrounding. Okay, how about 2? Oh, sorry. Sorry. Yeah, fine. Let's talk about 3 first. How about 3? Is Q greater than 0 or less than 0?
Greater than 0.
So
Absorb.
what?
Absorb the energy.
Absorb energy, that's why Q will be what? Positive. In this case, for the system. Q for the system will be positive. Q for the surrounding, for the system, will be what? In 1.
Negative.
Good, because it's less than 0. Good. Let's talk about the work here. Work of the system. Is this going to be positive or negative?
Negative. Negative.
Why?
The system does the work.
Exactly. How about the work of the system in this case?
Positive.
Positive. Why?
The surroundings does the work on the system.
Yes. The surrounding put the work on the system. Good. All right. Very good. Now, if we have a chemical reaction like this, in which we reacted this compound to make this one plus gas. Okay. And we keep the same volume. If we have this reaction, always there will be heat or energy with this reaction. This energy here, we did not change the volume. So the heat that will come out of this reaction, we're going to call it QV. What do you mean by QV?
Heat of the volume.
No, constant volume. See, the volume, we did not change the volume. If we don't change the volume and gas is formed, what will happen to the pressure?
Decrease.
Decrease.
Come on. You remember in chapter 6,
Increase.
we said, what will happen if we have gas, increase the amount of gas, and we keep the same volume? What will happen to the pressure?
Increase.
There will be increase. We call the heat that goes with constant volume, we call it QV. QV, this means constant what?
Volume.
Constant volume, but the pressure will change. I hope this is clear. So this is called QV. What do you mean by QV?
Constant volume.
Heat energy with constant volume. Okay. Now, what is the work in this case?
0.
No, there must be work, of course. There will be work, but it's delta PV. Okay. The change in PV. So there will be some work. Good. Next, let's do this reaction now. All right. In this reaction, we're going to keep the pressure the same. So pressure P1 here, it's still P1 here and P1 here. So when we do this reaction, we're going to call the heat that goes with this one as QP. What do you mean by QP?
Constant pressure.
Constant pressure. Constant pressure. Constant pressure. Okay. Now, of course, because we keep the constant pressure, the volume must change, because you cannot have the gas without changing the volume. So what will happen in this case? The gas will take place and there will be change in the volume. and we call this QP, the heat by reaction. What will be the amount of W? The W is equal to P delta V. It's the pressure times the change in the volume, which is this amount, change in volume between these dots and this one. This is called W, the work.
Why it's negative, Doctor?
Because, why? Good question. Why is it negative? You should tell me. Use this thing to tell me why is it negative.
Work done by system and surrounding.
Exactly. So this is the reason. That's why W is equal to what? Minus PV. Because this way it will be done by the system and the surrounding. Clear? Good. Next. Let's do everything. We know that delta U is equal to what?
Q plus W.
Q plus W.
W equal to what?
Minus P.
That's P delta V. Okay. Okay. If there is no change in volume, what will be delta V?
Constant. Zero.
Yes. What's delta V? What's delta V?
Zero.
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 Why? The volume is the same. V1, what's the volume here? It's still V1. What's the volume here? Also volume V1. And that's why, what's delta V, which is V1 minus V1, equal to what?
Zero.
I hope this is clear.
Zero.
Okay. But here, delta V, is it equal to 0?
No.
So the volume change, delta V, is the difference between this volume and this volume, which is this one. Clear? Very good. So if we have constant volume, what will be delta V?
Zero.
Zero. That will be V.
Also zero.
To 0. That's why QV will be equal to what?
Delta U.
Delta U.
U. At what's called constant what? Volume. Okay. Now, if the Q, we call it QP when there is a change, no change in pressure. Okay. QP equal to delta U plus delta P delta V. P delta V. Is P delta V equal to 0?
No.
No.
Why?
No. Because the volume will change.
Exactly. Okay. QP, which is at constant pressure, the heat at constant pressure is exactly equal to H, the enthalpy. So I want you to define to me now, what is enthalpy?
QP.
It's QP, or it is energy transfer at constant
Pressure.
pressure, at constant pressure. That's called enthalpy. Clear? All right. So QV equal to what? What's U?
Internal energy.
Exactly. Change in internal energy. But what's QP? Change in what?
Internal energy plus the change in volume.
Change in enthalpy. So QV equal to change in U, which is in change in internal energy. And QP is equal to what? Change in Enthalpy. Okay, read this with me. I want you to read it. What's QV? QV equal to what?
Change of internal.
Change in internal energy. What's QP?
Change of
Change.
Enthalpy. Good. All right. And that's why we say that actually at constant pressure, delta H is equal to this whole thing. Okay, good. Very good. As I said, always keep in mind that QP equal to delta H. Good. Now, if we have a chemical reaction, any chemical reaction is, we can consider to be potential energy like this. And at one place, we're going to put the reactant and product, or we can have reactant and product. Okay. Okay. Now, and this is chemical energy, and we're going to use enthalpy of reaction. Enthalpy of reaction is actually, enthalpy is potential energy, H, and we can represent it by this. If you go, if this is your system now, if you this is your system, and you go from here to here, is this, how can you go from reactant to product in A?
By again?
By, how can you go from reactant to product in A? You have to what?
Absorb energy.
You have to put energy inside from surrounding. So energy must come from surrounding. Okay? This energy, we're going to call it Q in this case. It is energy, but another type of energy, which is Q. In this case, the reaction will be what? What? Endothermic or exothermic?
Endothermic.
No. Okay. But let's look at B. If you go from reactant to product, what will happen to the energy?
Will release.
We will lose energy.
So this is your system now. The reaction is your system, and it will be released to the surrounding as Q. And in this case, this will be exothermic or endothermic?
Exothermic.
Exothermic. Now, delta H is equal to H of product minus H of reactant. Always delta means difference in reactant and product. So for case A, which one is having higher delta H? I mean H. Is it product or reactant?
Reactant.
What? In case A, which one in numbers? If this is, for example, in case A, if this is 700, that's or 600, let's see, any number. What will be A? Is it going to be greater than 600 or less than 600?
Greater.
Less than.
It is the same.
Less, right? Okay, let's say 400 in this case. All right, and in this case, if you go from delta H for this reaction for A, delta HA, is it going to be positive or negative?
Positive.
Positive. Okay, how about delta H for B?
Negative.
Is this clear? Because always the one at lower is smaller number. This one, maybe let's put another number, or let's put X and Y. Which one is greater, X and or Y?
X.
X is
greater
greater.
higher, and that's why delta H, which is equal to y minus x. Y minus x. Is it going to be positive or negative? It will be negative.
Negative.
Clear? Delta H is H of product minus H of reactant. Keep this in mind always. Product and reactant. Delta H will be positive when
Endothermic.
and delta H will be negative when
Exothermic.
Exothermic.
keep this in mind. Delta H is always positive when
Endothermic.
endothermic. Delta H will be negative when
Exothermic.
how
Doctor.
it's the chemical equation. We write it like this. We write it like this. CH4 plus 2O2 to give you CO2 plus 2H2, and delta H is equal to minus 890.4 kilojoule. First question, is this exothermic or endothermic process?
Exothermic.
Excellent.
Exo.
This is exothermic. Exo. Why did you say exo?
Negative.
Negative.
Because delta H is negative. Is there a relation between them? Yes, we can relate things by saying 1 mole of CH4 react with what?
2 mole of
2 mole.
O2.
Mole of O2 to give you
1 mole of CO2.
1 mole CO2 and
2 mole of
2
H2O.
mole H2O and minus 980.4 kilojoule of energy. Is this easy? Excellent. Now, if I have 10 or 1.4 anything, 1.4 gram CH4, how much energy I'm going to get in this reaction? I have only 1.4 gram CH4. What should I do?
Convert to mole.
Convert to mole. What should I do?
Divide with the molar mass.
Molar mass.
What's the molar mass of CH4?
16 point.
Bro, 16.02 gram CH4 and 1 mole. And then how can I make energy? Yes, 1 mole CH4
Minus 890.4.
up minus 890.4 kilojoule, and this will go with this will go with this, and your final energy will be kilojoule. Is this easy? Can you do that?
Yes.
Very good. All right. Now, rules for this reaction. Okay. If you have any energy like this one, H2O goes to H2O. What's this? H2O. What? Solid. Goes to H2O. Liquid.
Liquid.
Delta H is plus 6.01. Clear? Clear?
Yes.
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 Is this exothermic or endothermic?
Endo.
Endothermic. Endothermic. If you multiply the whole reaction by 2, what will happen?
The enthalpy will be double.
Exactly. You must multiply the enthalpy by 2. Okay. What will happen if I do this one? H2O liquid goes to H2O solid. What will be the enthalpy?
Change
Change the sign.
minus 6.01.
Minus 0.01 kilojoule per mole. How about if I have 4 H2O liquid goes to 4 H2O solid? What will happen?
Minus 12.
Minus 12.
Minus 12 points. 0.
Minus
4 times
minus 6.0.
minus 6.01 kilojoule per mole. I hope it's clear. Very good. All right. And that's why if we reverse any reaction, what happened to the sign?
Change it.
will change.
Okay, let's solve this problem. If you have this reaction, this is photosynthesis, what's happening in the plant. Okay, what do you understand from this plant?
it absorbs energy.
Yeah,
Endothermic.
okay, it is exothermic or endothermic?
Endo.
Endo. It's the first information. What's the relation? 6 mole react with what?
6 mole.
6 mole make 1 mole.
6 mole.
6 mole. Less energy.
6 more.
Okay, now if I want only 75 grams of C6H12O6, how much energy do I need?
We'll change it to mole.
Change to mole. Change. This is the molar mass of glucose, and we change it to mole. What's next? 0.416 mole glucose, C6H12O6. What should I do now to calculate the energy?
Multiply it by 2,803 over 1.
2,803 kilojoule divided by what?
1 mole of C6H12O6.
1 mole of C6H12O6. How did you know it's 1 mole only?
From the relation. From the equation.
From the equation. Give the answer quickly.
One,
Yes.
166.
117 times 10. 117.00. This is the energy. Good. All right. Okay, I will stop here. Or let me just define one thing, and we'll talk about it. Specific heat. Specific heat. What's the meaning of specific heat? Is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree C. And we specify by S, specific heat. The amount of heat required to release the temperature of 1 gram of substance by 1 degree C. Okay, heat capacity C, which is same thing like this one, the amount of heat required to raise the temperature of an object by 1 C, 1 degree. Okay, what is the difference between heat capacity and specific heat?
The first is for 1 gram, and the second
1 gram, the second for any amount. So we use C when we don't know what's the mass, or we don't know what's mass. What's when we don't know the mass. Okay, good. Now the specific heat is certain numbers for certain number, but what's the most important one, specific heat of water, you have to know this now, is 1 calorie 1 calorie per, of course, what? Gram degree C. You have to know this. Specific heat of water, I want to memorize this, is equal to what? 1 calorie per gram degree C. Can we make it in joule?
Yes.
Yes.
What is what?
4.184.
0.18
Joule per
gram
Gram.
per
degree C. That's the only number that I want you to memorize. And that's how you change joule to calorie. All right? Otherwise, the specific heat of certain elements is available here. Okay? This is the specific heat of aluminum, specific heat of gold, specific heat of graphite, specific heat of diamond, specific heat of all of these things. Don't memorize any number here. I want you to memorize number here, which is not available here. What's the specific heat of what that I want you to memorize?
water.
Of only water, which is what? 1 calorie per degree C, gram per gram, or gram degree C, whatever. Good. All right. Good. Okay. Now, Q, you have to memorize this number.
Can you take 10 this time?
Once again, yes, I will. Now, Q is equal to Sm delta T, or if we don't know specific heat, then, and we don't need the mass, then Q is equal to C delta T. I will stop here and I will take the attendance right away. Okay.